That's what the vote said.
That's what the vote said.
You're going to get the test.
Yeah.
One
I mean, if we're wishing things, I wish we didn't have one, but.
Well, you gotta test it.
This be a project based?
Sorry, you're gonna get tested. You can prove yourself. Are there any questions about any of the homework problems?
Yeah.
Last couple classes.
Yes, but it's being pulled up, so.
Which one is it?
The second one.
Which one is it?
It's
These are two.
I mean, but tell me what the content is.
It was d dt of y of t
All right,
plus.
you're talking about dy dt, right?
Plus 2y of t.
2y equals x, right?
Yeah.
All right, now, I'm gonna tell you one thing. You can do this with Fourier, but it's easier to do a differential with Laplace. If you do Laplace, you just change the s into j omega. So what I'm gonna say is this, we're gonna use Laplace, and then we'll change it to Fourier. And I'll talk about this. So for the first thing they want is the solution. Now, there are no initial conditions in this problem, if you look. With no initial conditions, when I take the Laplace transform of this, it simply becomes sy of s, right? The derivative with respect to t of y, transformed as sy of s. There's no initial conditions, so you don't have the minus y of 0, all right? Then you have plus 2 times y here of s equals x of s. That's simply the Laplace transform of both sides. After that, they want the response, which is the ratio of output to input, called the transfer function. So now what we want is y of s over x of s, and we term that h of s. Well, if you look at this, y of s, I factor out the s plus 2 and divide it into x of s, then I divide by x of s, and I get 1 over s plus 2. I want you to all take a look at that and make sure you understand the steps I've taken. This is a very straightforward, actually it's a problem you had in your mathematics courses and differential equations. It's very simple. You all agree? And again, when we have this, we want to look at the response. This is the first thing. So now we let s become j omega. And we do that, now we get h of omega here, and that's 1 over 2 plus j omega. Does everybody see? The only thing I've done is replace s with j omega. In fact, s is j omega plus sigma, so effectively I made sigma 0. That's all I've done. Now, if you want the response to this, that entails a magnitude and an angle, correct? To get the magnitude of this, that would be 1 over the square root of 2 squared plus omega squared. You all agree with that? Agreed? That's the magnitude. And then the angle would be what? Well, the angle on the bottom one is always the opposite. It's inverse tan of the opposite over the adjacent. Let me draw it so everybody can see this. If I have j omega here and I have 2 here, when I say the angle, I'm talking about that. Does everybody see that? Well, that is what? Theta would be tan to the minus 1, or inverse tan, of simply omega over 2. Does everybody see that? Right? Now, that means down here, you would put angle and you would put tan to the minus 1 of omega over 2. That's a 2 there. You all agree with this, class? Again, that's the angle, but I left it in the denominator for a reason. What happens when you take an angle from the denominator, an angular measurement, to the numerator? It becomes negative. So now the angle, this should be actually rendered as magnitude is 1 over the square root. And I'll put 4 plus omega squared here. And it's at an angle of simply minus the tangent minus 1. If you want to use atan, that's fine, of omega over 2. I asked you to plot both magnitude and angle, right? You're going to see this is very easy to do, but you have to be attentive here. When I plot the magnitude of anything, I want to show you the trick on this one. This is going to be the magnitude of h of omega. The first place you start is at 0. You evaluate the function when omega is 0, or any function. You want to evaluate the origin. You all see at the origin, just look here. It's simply 1/2. Does everybody see that? When omega is 0, it is 1/2, correct, class? It's painfully obvious. So it's 1/2 here. Now here's the trick. Listen, when omega is 2, then you have 2 plus J2, right? That's called the 3 dB point. It's when now the magnitude of this is going to be equal to, really, it's going to be 2 times the square root of 2. You take either one of those and multiply the square root of 2 and you're going to get it. It's going to be down by 70% when you take square root of 2 over 1 over square root of 2 is 0.707. Do you all remember this, class? So these are called the 3 dB points. Now at 2 and at -2, it's going to start rolling off. It's going to continue to roll off. And this point is going to have a magnitude of 1 over the square root of 2 times 1/2. It's going to be 1 over the square root of 2 what the peak magnitude is at omega equals 0. Does everybody understand this? You can prove this yourself. You all agree with this, class? Give me a show of hands if you do. Do you see it back there? Or not? Well, just look over here. Take a look at this just for a second. If I have 1 over 2 plus J2, think about this just logically. Isn't the magnitude of that 1 over, and then I can say, I can square this, take square root, right? Square this, you get 4, square this, you get 4, right? Add them up, you get 8. What is 8? Well, go ahead.
Are you squaring the J as well?
Remember, we had this discussion. When you take magnitude, you ignore J. You take, because these are at 90 degrees to each other, right? You take the real part, square it, the imaginary component, square it, and then take the square root once you add them up, right? Y'all remember this, class, when you get magnitude? So here, what is this? Well, if I have 1 over 2 plus J2, isn't this really 2 squared plus 2 squared square root of that? Correct, class? All right, what's the square root of 2? I mean, if I have 2 squared there and I come out, I have 2, and then I have, this becomes simply 1 over 2 root 2, doesn't it? Just do the math. You all see that? It's straightforward, right? You factor out the 2 squared, you get 2, and then I have 1 plus 1. 1 plus 1 is 2. It's 2 root 2, right? It's over 1. So it's what? It's reduced by 1 over the square root of 2. This is actually, it's 0.707, the peak value. It's called the 3 dB point. And write that down. It's the 3 dB point. And it's the point where the voltage drops by, or current drops by 1 over the square root of 2, and the power is 1/2. It's called a half power point, usually. Now, this is a symmetric plot, so it'll do the same thing over here. And that's the h of omega. I will ask for sketches on tests of these type of things, just to make sure you know what you're talking about, okay? It's a simple thing. You always, when you're doing a sketch, evaluate it at the origin, the function at the origin, evaluate it, if possible, at the 3 dB point, and where does it go as omega goes to infinity? Just take one look at this. What happens when omega goes to infinity?
0.
It goes to 0, right? The magnitude goes to 0, and in fact it does. If you had to determine that in terms of a filter, what kind of filter operation would that be? Well, it is in a sense, but it's a low-pass filter. It's centered about the lowest possible frequency, 0. It's a low-pass filter. Y'all understand that? A bandpass is usually not at 0. It's when you shift it out at some frequency, and then you have a pass band over like a plus or minus frequency range. You follow me on that, class? This is real important. Now, what about the phase? The phase of this one is just as important in some respects. So if we take the angle of h of omega, I'm going to show you how I do this. This will work right here, inverse tan. You're not used to working with inverse tan a lot, I don't think. Maybe you are. What I do is just look at the function right here. If I have 1 over 2j, what's the phase of this when omega is 0? Well, I have 1/2, don't I? What is the phase of a positive valued number? Well, it's just 0, right? If I have 1, it's at an angle of 0. That's an assumption because there's no imaginary component, correct, class? All right, now what is the phase of this when omega goes to infinity? Well, now I have 1 over 2 plus j infinity, right? Or really, don't I have about that 1 over j, omega is omega large? Well, what's 1 over j? Is it minus j? What's the phase of minus j in radians? Minus pi over 2, or minus 90 degrees. Do you all see that? So what I can say here is the phase is 0 here. It's going to go to minus pi over 2, or minus 90 degrees. What is does it do in the opposite direction when all of a sudden I take a look at this function, 2 plus j omega, and I let omega go to minus infinity, right? As it's going there, isn't it about like 1 over j or minus j omega, correct, class? As omega goes to minus infinity, what's 1 over minus j? Plus j, what is j? Phase of j is?
90 degrees.
Plus 90 degrees. It's doing the exact opposite. So I know as it's going to infinity, if this is omega, it's going like this. And the point where it transitions to be 45 degrees is going to be at -2 and +2. And that's at the 3 dB frequencies. We can prove that if you want, but it's self-evident. And it looks like this. That's the phase. Does everybody understand what I'm talking about? Give me a show of hands if you do. Do you have any questions about it? You all see this? I always, yeah.
Why is positive 90 in the second quadrant? Did I miss something?
It's not a unit circle.
What are you talking? This has nothing to do with the unit circle. This is omega, and what you have is this is going to go, just look at this. Take a look at this, and let me give you a for instance. What if I have 1 over 2 plus j 500? Okay? That's, I mean, minus 500. Sorry, minus 500. I'm going in the negative direction, right? Can you all see this, class? Isn't that about that? All right, what's 1 over that? Isn't that positive j 500?
Yes.
How do you render that? Isn't that 500 at an angle of 90 degrees or an angle of pi over 2? It's going to, this is going to pi over 2. Or 90 degrees. Or 90 degrees. Now please make sure you see this. You'll be asked for magnitude and phase plots of simple functions. And believe it or not, a lot of people are not used to doing this. When you had circuits, I don't know, when I taught circuits, I didn't force this issue on people. I may have mentioned it in passing, but you have to be aware of this. In your laboratory work, do you have to do magnitude phase plots? Not yet. Have you had your circuits lab? Okay, well, you're going to get them in some lab, and I don't know which one it is, unfortunately, but you have to be aware of this. This is very important to be able to do this. Do you all understand what I've done? All right? And this is just common for any kind of analysis of a system. You look in the frequency domain, you see the transfer function's properties, how it behaves, magnitude and phase. Now, the next part of the problem was, I did that. Did they want the impulse response? Let's get it anyway, if they didn't. All right, if I have this differential equation, I want the impulse response, it means x of t becomes delta of t, correct, class? And really what I do is this. Since I have h of omega as 2 over, I have this, h of omega is equal to simply 1 over 2 plus j omega, right? When I go back to the other domain, this is the simplest one of all, what is it? It's e to the minus, come on, 2t u of t, isn't it, class? That would be the impulse response of the system, or h of t. You can do it in the Laplace domain too. What is, if this is 1 over 2 plus s, automatically you know it's e to the minus 2t u of t, don't you? It's better be instinctive by now. Just think of that. That's the same thing with Fourier. But make sure you put the u of t. Because if you just leave that and not have that, that goes to infinity as t goes to minus infinity. So you got to make sure you put the u of t there. That limits it. Now, the next thing I ask for is when I give you x of t as a value of, I forgot what it was, e to the minus t u of t,
Yes.
I think. So let's do that part. This is a good problem, by the way, really good problem. And one other thing I'm going to tell you about this, sometimes graph paper helps when you're actually plotting things, or engineering paper. You all remember those green engineering tabs? Do you guys still use those or not? I mean, it helps if you're plotting things to have crosshatch paper. It really does. Helps me at least, because I'm poor at sketching to begin with. So the next thing is this. We're going to let x of t, the input to the system, be equal to e to the minus t u of t. Now you might as well just do this in the Laplace domain. There's no reason to do it in Fourier. And there's no, I will never confine you to do it just with Fourier or just with Laplace. You've got to understand, you can't use Laplace when it has values that are non-zero for t less than 0, so it automatically disqualifies. If you'd use Laplace or something like that, then you'd really you really failed bad, miserably at that. But here, when I have this, I can go instead that means x of omega, or better yet, let's do x of s is simply equal to 1 over 1 plus s, correct? Agreed? Now, I know my h of s is equal to y of s over x of s, and it's equal to simply 1 over s plus 2. That's what it was from the first part, right? Now, if I want to get my response, y of s, when the input is x of s, I multiply both sides by x of s. And now I have my output, right? That's what I'm trying to show you the simplicity of this. Do you all agree, class? What happens right here? Let me see if I can get a darker marker. Well, now, what I get is what? I get my y of s in the Laplace domain, it could be a y of omega if you want, is just equal to 1 over s plus 2 times 1 over s plus 1, correct? That's the output of the system in the Laplace domain for an input of e to the minus t u of t. Everybody? All right, well, how do we solve this? We want to go back to time. What do? Partial fractions. Let's just do it together. We have a over s plus 2 plus b over s plus 1. Those are the poles. Do you all agree? All right, how do I get the first value of a? What do I do? People? Where's the pole at a, for instance, the denominator? S equals minus 2, correct? So I cover this up, and I evaluate the remainder at s equals minus 2, correct? What is that? 1 over minus 2 plus 1 is minus 1. Do you agree? So that just means this one's minus 1. Want to take a guess what the other one is? Almost guaranteed. Matter of fact, it is guaranteed. Now if I cover up the s plus 1, right, and I let s equals minus 1, what do I get? 1, don't I? 1 over minus 1 plus 2 is 1 over 1 is 1. All right? Now I have that. I'm in the S domain. I have partial fractions that are very simple transform pairs that I understand. What does it go to in the time domain, class? Well, what's this one go to? Well, better yet, let's take this one first. It's going to be what? E to the minus t u of t, right? Minus e to the minus 2t all times u of t. Do you all agree with that? Now that's one of those things that's called a double exponential response. I'll tell you what it looks like. If you have y of t here, where does it start at t equals 0? What's the value? When t is 0, I have 1 minus 1. It is 0. Do you agree? Where does it go to as t goes to infinity? As t goes to infinity, that's 0 and that's 0. It's going to 0 infinity, right? Somewhere along the line it has a little bump. And what it does is this. Something like that. If you wanted to find that time where the maximum occurs, how would you get it?
Take the derivative.
Yeah, and I'm going to tell you one thing. Ignore this when you take the derivative. So you would take the derivative with respect to t of e to the minus t minus e to the minus 2t, right? That's first thing you're going to do. You're going to get minus e to the minus t, right? Minus, and this is going to be plus 2 e to the minus 2t. That's the derivative of that, correct, class? You set it equal to 0. Now you find that time. Do you all follow me on this? What do we do here? Well, I'm going to have to sort through this. I'm going to just take I'm going to take e to the minus t on that side. So now I have e to the minus t on that side. And what do I do with the rest? Say again?
ln.
A log of it, yeah. Natural log of both sides. And I get natural log of 2 e to the minus 2t equal to natural log of this is just going to be minus t, right? Then I can break this up into natural log of 2 times, or minus 2t, correct? Just watch. Do y'all agree with that? Right? Log of a times b is log a plus log b, correct, class? I hope I'm not that far. You're just tired? I hear you on that one too. So now what I'm gonna do is simply take the minus 2t to the other side, becomes plus 2t, with a minus t is just t, right? And that means 2 is equal to log of the natural log, or t is equal to natural log of 2. So this is just, this point right here is equal to natural log of 2. You agree? And if you want the actual peak value here, you put natural log of 2 in here, right? What do you get? Well, e to the natural log, or minus natural log of t is just what? Well, I'll tell you what, don't worry about it, but do you understand what I'm doing here? That's what you would do in a sketch. You don't, I'm not gonna probably ask for that, but you, this is how you would do it. Because it was a, is there anything else in that problem?
No, I just said find y of t for the.
All right, now that's the way you do it, and I'm gonna level with you. To me, this seems very simple compared to some of the things we've gone through with convolution and stuff. This is a very simple problem, but you have to understand how you do all aspects of it, from the phase plot to the magnitude plot, to h of t, to getting y of s by partial fractions, and then y of t by doing an inverse transform pair. Follow me? Other questions? Yeah.
Could you do the sine pi t over?
Yeah, I'm gonna do that one because I didn't do, I'm gonna show you the trick in this one. All right, I wanna do that one. I'm gonna level with you, that's a harder problem, but it relies solely on duality. And I'm gonna do it in its entirety, I'm gonna do it slow, and don't feel stupid if you don't understand something, ask the question. I'm trying to be very frank with you, I'm here to help you, not hurt you. I'm trying to help you become good engineers, I'm not here to weed people out, all right? This is not what I'm about. I'm trying to make sure you learn this stuff, and I'll tell you really why. Because when I get kids in radar that don't know how to do this stuff, it really frustrates the heck out of me. Anybody takes my radar class, it has me for this. You're gonna, if you pass it, you're gonna know how to do it. And I'm gonna make sure you do. So now, the functional form that they wanted to transform of was sine of pi t over pi t times sine of 2 pi t. And is it over 2 pi t? I don't remember. All right, we're gonna make it over pi, so let's say pi t. Here's what we're gonna do, very first thing. That's the function they want the transform of. Follow me? Well, they want the Fourier transform of this. Right off the bat, I'm gonna multiply by 2 here and multiply by 2 here. Now, the reason I'm doing that is this. I know that the sinc function of x is defined as sine of x over x, correct? That's the definition you have to know. Do you see how now this is of the form of a sinc function and x is pi t? This is of the form of a sinc function and x is 2 pi t. Do you all see this? So now I'm going to render this as simply 2 times the sinc of pi t times the sinc of 2 pi t. I want to make sure that's the function. You can call it anything you want, but that's it. Are you agree? Now we use duality at this point to get where we're going. We're going to have to do convolution, but duality is the key thing on this. So let me take you through this. Anytime I think of a sinc function, I think in the other domain, it's a pulse function. Let me just take you through it. The pulse of with tau of t, how many know this? Transforms, Fourier transforms to, anyone?
Tau.
Tau, the weight tau, right? Times the sinc of omega tau over 2. Agreed? I have to know that functional transform pair. Now we use duality. And if we use duality, duality says if this is my x of t, and this is my x of omega, I take this one into the time domain and I replace omega with t. So it becomes tau times the sinc of t times tau over 2. And then I take the time domain function, and what do I put there right away?
Minus, or 2 pi.
We have to put 2 pi first because of duality, understand? So 2 pi has got to be here first. And then what do? We take t and make it, class?
Negative.
Minus omega. So I'm going to put it in p of tau of minus omega. Now, What do you know about the pulse function? It's an even function, right? Looks the same on at the negative axis as it does in the positive in magnitude, right? So what I do is just make that. It'll, yeah.
And you can do that because it's centered at 0. If it were time.
You just replace whatever this function is minus omega, right?
Mhm.
Now, what you're really getting at, well, what if some of it, if p of minus that function is not equal to p of plus of that function, you leave it at minus that function.
Okay.
All right, maybe if it's an odd function, then you pull the negative sign out and it'll leave omega there. But that's, I think it's fairly intuitive if you think about it. Just make sure you put minus omega first. All right, now in this one, what happens? Well, I want to scale this thing so that the coefficient of this function is 1. Got me on that? So I go ahead and I take tau over here. And now I know the sinc of this is equal to that, right? Agreed, class? Now let's do this for the two functional forms we have. Keep an eye on me here. So the first functional form I had was the sinc of pi t, I believe, correct? And I want the transform of that. All right, so you take the coefficient of t here, which is pi, and you set it equal to the coefficient tau over 2. Does everybody see what I'm doing? Then you calculate tau, and that makes tau for this one equal to 2 pi, right? Tau over 2 equal pi, that means 2 pi equal tau. Correct, class? Everybody see this? I gotta make sure, I'm looking at people, some people aren't sure of this. You good, everybody? How many see this here? I gotta make sure you see it. All right, now what do I do? Well, now I come over here and I see that now I take 2 pi over tau. Well, 2 pi over 2 pi is 1, and it's p of tau. Tau is 2 pi. So I put p of 2 pi of omega is the transform of that. Does everybody understand that? It's straightforward, using duality, correct? Duality is key, and you're going to use it and use it and use it and use it all the time. What's the next one? The sinc, right, of 2 pi t goes to what? Well, now for this one, what is tau? Or 2 pi is what? Equal to, say,
Tau over 2.
tau over 2, or tau is equal to 4 pi for that one. Do you agree? Take a good look, right? I see suspicious looks. Do you all understand? Yes, sir.
Can you go over how you got tau again?
Tau? Sure. When I look here, you see this transform pair? All right. Now, what is the coefficient of t? It's tau over 2, isn't it? Over here, what's the coefficient of t? It's pi. So pi equals tau over 2, therefore tau is 2 pi for the first one. Agreed, everyone? You all see this? What about the second one here? Well, I come over here and I see I have 2 pi over tau in the frequency domain. My tau is 4 pi, so I have 1/2, don't I, class? So I have 1/2. And then I have this times p, and now it's 4 pi, that's the width of omega, right? So now we use the property of multiplication in time is what? Convolution, but what, you have your books there? I want to make sure you see the property. I do this with my book, and I encourage you to do this. I put a tab on important pages. This is where the tables are in this book. The old book we had the tables on the cover, on the inside front cover and back cover. They had Laplace and Fourier properties and tables. I like that better, but here they don't. So I flip to here, and the property I'm looking for is, when you see this is multiplication in time and they want the transform of it, it's the last property, no, I'm sorry, it's the property on page 229, and it's the second to last, it's property 12. It's 1 over 2 pi. So this becomes, I'm going to go ahead and say the 2 I'm just going to take with me over here. Do you understand that scales, right? This is going to be my first function and second function. So it says you take that divided by 2 pi, And then you take the first functional transform, Fourier transform of it, which is P of 2 pi of omega. And you're going to take that and convolve it with the transform of the second function, which is P of 4 pi of omega. Do you all agree with me? That's the operation we have to accomplish. It's not a hard one, though, and I'll show you why. In general, convolution's bad. This one isn't. You all see I can cancel the 2 on top and the bottom to make life a little easier to see. So I can get rid of that and just say this is really 1 over pi, right? Now I have to convolve these two functions. Do you agree with that? Let me show you how to do this, and you'll like it. This is how I do. Anytime you have just, I call them rectangular blocks that you need to convolve. You have one of with 2 pi, one of with 4 pi. Yep.
I thought the pi already was gone.
For what?
Like, where'd the pi come from?
Do you have your book?
Is this just for the?
This, I'll show you the property so it sticks with you. See, when you do convolution in time, if I have x of t convolved with y of t in time, in frequency it's just x of omega times y of t, right? But when there's a multiplication time, x of t times y of t, when you want the transform of that, then it's 1 over 2 pi
Oh, okay.
from the convolution. Here's the property. Right there. 12.
All right.
Yeah, I encourage you to bring your books always and write in your books. This you won't lose usually because it costs so much. I'll lose my notes all the time or rip them up anyway. So now back to this. How do we convolve this thing and make it make sense of it? Let me show you the trick.
Question, shouldn't there be a 1/2 in front of the pulse of 4 pi omega?
Remember when we did this?
Or did they cancel out?
We had a 2 and I had divided by 2, right? And I canceled it. Didn't I, class? You all remember that? You can take a look at the steps, but what I try to do is, because I know I have a 1/2 coming in there, it gets rid of that when we do this. But wait a second.
Because if all we
Hold on.
divided by 2 pi.
Let me do this again, make sure. First I have, when I take the 2, I'm gonna leave it as 2 over here, and I know it's divided by 2 pi. I know that for a fact, right? Now, this one, yeah, I got a 1/2. You're right, you're absolutely right. So it's 1 over 2. It's gonna be 1 over 2 pi. My bad, you are correct. Are you ready? Thank you for catching that. Now, we're gonna do the convolution.
Wait, hold on, why is isn't the 1/2 only on the 4
Four
pi
pi.
pulse?
Let me
So
do
wouldn't
this
it
one
be-
so you can see it. Right here. This is the property of it, right? X of t times, and I'll call it h of t. Transform of that is 1 over 2 pi times x of omega convolved with h of omega, okay? That's what it is, all right? Now, our x of t was 2 times the sinc of 2 pi t, right? And then it's time, or just pi t, and then sinc, right, of 2 pi t, right? All right, follow me on this one. There's a 2 in front, right? So what I'm gonna do right off the bat, I'm gonna say I have 2 pi, I have 2 over 2 pi. I simply carried that over, I've taken care of this. I've accounted for it right here. Got me? Now the next thing I do is the transform of this. That is what? P of 2 pi of omega, correct?
Yes.
Then I do the transform of the second one. That's P of 4 pi of omega divided by 2.
Yes.
All right, now, I guess I can do it this way if it helps. But
I see, okay.
then it's gonna have a 1 over 2 pi no matter how I cut the cake.
Okay.
All right.
Okay.
That's gonna be out in front. That's a scale factor, by the way. It's not that big a deal. But when I do the convolution, I'm not gonna worry about the scale factor. I'm gonna show you how to do these boxcars easily. Luckily, these are both the same height. When you're convolving two functions, first you look at it in the domain, in the omega domain, and one of them looks like this. Height 1, call that x of omega. And the other one, minus 2 pi, right? Height 1 goes to plus 2 pi, all right? Now when you're convolving boxcars, this is a simple way. You can just use that top one right there as the base, and I'll show you. When we get the convolution of these two, x of omega times, and I'll call this y of omega, it doesn't matter what it's called, times convolved with y of omega. How many have used that little Java applet where you can actually draw the functions and movements, see them convolve together? How many have used that? I encourage you, if you have not used that, to use it. It will help you immensely see what I'm doing here, if you don't. So what I do is, I have to first take this function and shift it all the way down here, and I'm going to do it. So I'm going to take a look at this. And when I shift that thing all the way down, it's going to be at this base. All right, now I have to shift this down to here, right? Just so these edges are about to touch right here, right? You all see this? And as I convolve that, as it's going to go through, there's more and more area that's going to increase until I go through the whole thing, and then it's a constant amount of area. Do you all see that, the overlap area? And then as it moves through, it starts falling off, and it will be symmetric. Now, I've told you a trick about these. You know that these are both finite width pulses, right? Your result when they're convolved will be the widths of the first plus the width of the other. The first was 2 pi, the second was 4 pi. The total width will be 6 pi. You with me? In order to start this thing, it will start at minus 3 pi. And here's why. This starts at minus 2 pi. This starts at minus pi. It always starts as the sum of the two, you might say, most negative points. Right? So it's going to start down here at 3 pi. Now just watch this. I'll show you the general shape. Think about that. So I've got this thing. I bring it down here at 3 pi, right? It goes through. It's going to keep growing until I hit pi. It goes 2 pi and it's growing. So it's going to be growing until right here when I hit pi. It's going to grow from minus 3 pi to pi. Then it's going to flatten out. And it'll be symmetric about this axis. This one is going to be pi, and then it will fall down at 3 pi. The total width is 6 pi. Now we're going to get the height. Are you ready? This is an easy thing to see. Remember, I'm doing just the boxcars. I'm not scaling by 1 over 2 pi. Just watch this. Now we know that this area has to do when this is immersed in this, correct? Well, what would the area be? It's 1 times 1 is the height. The width is 2 pi. You all see that? So this height is just 2 pi. And now you've got the shape of the two boxcars. Do you all see this? If I want what the actual value is, I divide by 2 pi, don't I? You see how there's a 2 pi? This is a beautiful thing. Now the convolution of these two functions, right, with it divided by 2 pi, has a height of simply 1. Now, how do you want to represent this function? I'll tell you, probably the easiest way, and some of you can see this. Doesn't this look like a triangle there? Are you with me? A triangle from minus 3 pi to 3 pi, right? And what happens? Well, between minus pi and pi, it's looking like, if this is minus pi to pi, doesn't it look like we've added a negative triangle to knock the top off? Do you all see that? Right? Add these two together. What will you get? Don't you get it? The top gets knocked off. Do you all see that? Let's get the values. So what I'm going to do is say the mathematical statement for this will be triangle function of with 6 pi of omega. I'll get the constant in front of there in a second, and I'll just put it times a plus, or it's actually going to be minus a pulse function of with 2 pi centered at omega. With me? Now, the one thing I want to tell you is, I know that when omega equals 0, that this has a height of 1, right? You all with me on that? At omega equals 0, it has a height of 1. Well, at omega equals 0, the triangle function has a magnitude of 1, doesn't it? Remember the triangle function, class? Yes?
Why are we subtracting a pole?
I'm sorry. Triangle. Thank you so much. That is my fault. That's supposed to be a triangle too. They're both triangles. I'm going to get the weight on it. I'm going to leave this as 1. So we're going to say this is the functional form I want. Now here's how we get A. Do you all see at 0 it has a height of 1? You with me on this? So I know that A minus 1, because that's 1, 2 magnitude, is equal to 1, or A is 2. Do you all see this, class? So now you go ahead and you can say that this is the functional form. If you wanted a mathematical statement of that, and that would be my convolution of the two, whatever you want to call it. This is equal to the convolution, so this is the overall response. And it's x of omega convolved with my, whatever I had there, y of omega over 2 pi. And I think, did I provide an answer for that one, or not?
I don't think so.
Well, that's what the answer will be mathematically, it's that one. This is a famous problem, by the way. Okay? I know it seemed kind of long, but you have to follow the details. You have to appreciate the details. I would probably just want to sketch. I wouldn't want a mathematical statement, because the sketch will do it. Once you do that, you say everything. Other questions before I go? Oh, we got about, what, 10 minutes? All right. I did want to do that one, and I wanted to do that one, because this worked perfectly in my lecture. Now, we're going to talk about filters. And did I give you the lecture about causality? What filters are? No, I didn't think I mentioned it yet. Between you and the radar class, we're like talking about the same material, only the application is much different already. So now what we're going to talk about is filters, the responses, and some things that can't be, or you can't actually realize them in real time. I need to talk to you about this. This is important. And then we'll get into sampling. This is just brief right here. So a question is, suppose I want to filter response, can I actually build a filter to do that? Digital filter or analog? And let's say I want this. I want h of omega in the frequency domain. So now this is called synthesis. I'm synthesizing a circuit or an algorithm to do this filtering. And this is a classic low-pass filter. It'll be at minus the bandwidth over 2, bandwidth over 2. This is in the omega domain. And the width of this is just b. I'm going to make the height 1. You all see this, class? And let's assume phase doesn't even enter into this, okay? We're not even going to worry about the phase. And I want to know, when I have a filter that looks like that, if I have input x of t, usually they do it this way. They have an h of omega here, and they want the output y of t. They just are doing it this way. They could put an h of t here, but they usually put a filter response, and they usually sketch it, what it looks like. So if I do this, the first thing I always ask myself to see if it's feasible or not is if you put a function in delta of t, that's an impulse, your output would be h of t. Do you all agree with that? The impulse response is h of t. So what does it look like? Well, how would I define this in terms of a mathematical function anyway? Think of yeah, a pulse function of width b centered at 0, right? That's a low pass. This is the most classic low pass filter. It's called a block filter, really. Sharp edges, no fall off. The other one had those nice round corners and stuff like this. This doesn't have any of that, and there's no phase. Now, is it feasible to build something or create something like that? And this isn't continuous time. And you know the reason why? Well, you're about to find out. It's causality. And here's why. When I take a look at this, I want the transform of p of b of omega. I want to find out what it goes into the other domain, right? So here we use duality, and I'm big on duality. I know that a pulse function of width t, we just did this, by the way, it goes to tau, right, times a sinc of omega tau over 2. These you must know. You with me? I'm going to go through it slow here. Everybody got that? That has been done probably 20 times, 30 times in this class. Now we use duality. We take the mathematical form of the transform in the omega domain and replace omega with t. So it's tau times the sinc of, now it's going to be t tau over 2. And here, now I'm going to get 2 pi. Don't forget that 2 pi right off the bat. If we were using a transform that was defined in F, you wouldn't need that. But here, you've got to have the 2 pi. And then you replace t with minus omega. Make sure you're used to writing minus omega. We know we're going to make it plus omega. Just get used to writing it, okay? And do a bunch of these too. Now, make that that. And I'm going to do one other thing. I'm going to scale by 2 pi. So I'm going to go ahead and take this tau by 2 pi here. And now I have the inverse transform of the pulse function. Do y'all see this? In the time domain. So that means it goes to tau over 2 pi. Tau is b, isn't it? Correct? Divided by 2 pi times the sinc of, now it's t times b over 2. You all see what I'm doing here? I'm simply replacing the tau with b, correct? So now this is the transform of the pulse and frequency into the time domain. I usually put time on this side. I got lazy, just left it over there. Got me? What does that look like? I want you to think about this. What does this sketch look like? If we just took the magnitude of this, of b over 2 pi times the sinc of tb over 2 versus time. Well, the sinc function when the argument is 0 is 1. So here, the height would be b over 2 pi. Now the sinc function has the first 0 when it goes to 0. This is when the sign of the argument goes to 0. Well, when does this argument go to 0? Sign goes to 0 at pi, isn't it? So the first 0 is pi. Well, what does that correspond to in terms of t? It would be t times b over 2 equals pi, or it would be t is equal to 2 pi divided by b. Do you agree with me? First 0 is somewhere over here, whatever that is, 2 pi over b. It's a symmetric function, so it minus 2 pi over b is a 0. And it looks like this. And by the way, this height is minus 13.2 dB below that height on the sinc function. It's the first sideband. You'll get this later and more frequently, but just remember it's 13.2 dB less than the peak. Now, when I look at this function, this is the eerie thing. This is in the time domain, right? What caused this function? A delta function like this in the time domain, correct? Now, I want you to think about this logically. This is negative time, right? Before the event happened that created it, it's already spitting out output. It's anticipating that function. Do you follow me on this? That's impossible. That's a non-causal response to an impulse response. Y'all see? That's negative time. Take negative 5 seconds. There's something there, but the input didn't happen. How does it know it's going to happen? It doesn't. That's an impossibility. That filter you can't build. All right? Now, the truth is you can build that filter and use it if you have recorded data. When I was at Penn State in Space Science Laboratories, they had huge data records. They put up things, satellites, they put up other stuff that were atmospheric probes. And for atmospheric electricity, you're doing a lot of work. You're measuring Schumann resonance and all these other things that are electrical events in the atmosphere. As well as if there's as lightning, for instance, causes electromagnetic transients in the atmosphere. Nuclear weapons do, solar flares, all that stuff. But they had a data record for maybe a month. Now, if you wanted to filter out and look at specific amounts of energy in certain domains, you could do a block filter because now you have the data record. You know when everything happens, so you can filter and extract information. You follow me? But if you don't have a data record, if it's real-time data processing, you can't build that thing. It's non-causal. Got me on that one? And this filtering is used extensively for recorded data and other things, but it is an impossible filter to actually build in real time because it has to anticipate that something's going to happen. And it's impossible. I'm almost over. I got a minute. All right, let me tell you where we're going. I'll give you a few more problems. But what I'm going to do is this. For the quiz on Friday, it's going to be on Fourier transforms. I'm probably going to give you something that requires you to use duality. So make sure you know the duals of both the pulse function, all right, and the triangle function. All right? I want to make sure you know how if you have triangle pulse in time, what the transform is, triangle pulse in frequency, what the transform is. Got me on that one, class? And make sure you know how to build functions, like how we built that function, you know, out of two functions, okay? And any other questions? We're going to do sampling. I don't have enough time today to really even start it, but sampling is now something that's critically important for engineers, because what do we do all these days? Do we use analog anymore, really, for anything? What do? We sample a signal, then we store it as a digital, we first quantize it, so we get quantization error, then we store it as an 8, 10, 12, 15-bit number, right? It's in binary, and then we do our signal processing, and that's where I'm going. By the way, the first thing I learned was analog stuff. I mean, I even learned vacuum tubes when I was in high school. They still use them for things like klystrons and ignitrons and stuff like that. I mean, well, really, pentos and ignitrons, but nowadays, only the Russians use vacuum tubes in aircraft because they're immune to EMP.